Now in this video we are going to derive the stiffness matrix for standard beam elements. So first of all, let's make sure that we know what standard beam elements are. Standard beam elements basically reflect beams that follow the Euler-Bernoulli principles. So in general, you will have beams that are going to bend only. So that means there will be pure bending. So that doesn't look very pure bending sort. There's also some kind of stretching going on. But that's the speciality of standard beam elements, that we are only going to look at pure bending. So in the finite element formulation of any kind of element, we always start with describing the approximate behavior of the element. And since we have already been introduced to shape functions and how we set up the shape functions, we would like to start doing the same for the beam. So once we describe the approximate behavior of a beam by means of shape functions, we will be able to set up the general stiffness matrix for the standard beam formulation. Now, to derive the shape functions, we have to always identify the number of degrees of freedom in the system. Because the number of degrees of freedom in the system are always equal to the number of shape functions that we need to derive for a certain element. Now, as you have already figured out, the easiest approximate behavior is done by means of assigning a polynomial or any other permissible function. So I'm going to use a polynomial function because they are simple, identifiable, and can be easily worked out. As a simple rule, if the number of degrees of freedom in a system is n, then the order of polynomial should at least be n minus 1 to start with. Another rule for any function to be used as a permissible function to describe the approximate behavior of a beam element or any other element is that it should be continuous first derivative. So the function should always have C0 continuity. So now let's look at, so therefore what we are going to do is describe the approximate behavior. So in terms of approximate behavior, what we already have decided is to define shape functions. And for shape functions, what we need implicitly are number of degrees of freedom in the system. So let's again draw this beam element. So you have a nice beam element here. This is a single element. I'm just drawing it like this, or although you would, when you make it in finite elements, you will still see it as a wire, which is shown on the right here, like this. But here we are going to look at it as just a cross-section sort of thing. So it's easy for me to make some notations and drawings on it. There are some rules that we are going to follow. We will use the local axis like this. And then the global axis, of course, can be here somewhere. So you have capital X, capital Y. The length of the beam is given as L. You can have capital L, small l, doesn't matter. And because it's a single element, there are two nodes, I and J. Now, because this is an element which is under pure bending, there will be distinct degrees of freedom that will act on this element. The first degree of freedom is going to be a transverse displacement. As you can see in the top right figure here where the bending is shown, of course this is a much exaggerated figure, so it's not a really nice representation. Should probably draw it out again. You would have bending, which will look, again, bad representation. If you have the neutral axis over here and I have bending, then the neutral axis, say suppose bends like this. You have your new beam in this way. This is again stretched a little bit. That means this point has moved here. We draw it in a different color. So this point has moved here. So there is a vertical displacement. This point right here has moved here downwards. This point has again moved here. So sorry, here, this is not a very good picture. So if we look at these two parts here in the drawing, this one and this one, then we can see that there is vertical displacement that's happening. So therefore there will always be this degree of freedom which is going to be vertical, or called transverse displacement. So here you will have u I1, and at this node it will be uj1, and there will be a second degree of freedom at each node, which will be to do with rotation, because under bending you will always have rotation. As a convention, we always use anti-clockwise rotation as positive, so I also draw it the same way in the pictures. So that is ui2, and in this case uj2. So that means now we have described the element that it is under pure bending, therefore it will undergo rotation and transverse displacement, because all the points will always remain plane. So all the plane after deformation will always remain straight and perpendicular to the neutral axis. Now for ease of writing, sometimes we can also say that the transverse displacement ui1, uj1 can also be written as v1, v2. Sometimes we don't have to use it like this. Those are transverse displacements, and the rotations ui2 and uj2 are derivatives of these of the transverse displacements. So rotations are then written as dv1 dx and dv2 dx. That of course comes from the curvature. You've already derived that or seen that in case of standard beam formulations that we saw in the previous video. So now you can see that the element has been defined in terms of number of degrees of freedom. So the total number of degrees of freedom n is 4. Therefore, the minimum behavioral approximation that we can pick for the element in terms of a polynomial function is going to be of the order n minus 1, which is basically equal to 3 in this case. So we can say that the assumed displacement function for v, because that's basically ui1 or uj1 can be taken as v1 or v2. We can also just write it as v, can be expressed as v is equal to c1 plus c2x plus c3x square plus c4x cubed. Now of course this should be permissible, therefore it has to support all the boundary conditions, and it has to be C0 continuous. Now the shape function can be derived in the method which is very similar to the one that is shown in the previous videos and the previous weeks. Now what we need to do here is that we have certain conditions that we know of from the boundary or from the element. We know that there are points I and j, and in the x coordinate we can mention those points as xi and xj. Now if we say that xi is equal to 0 and xj is equal to L, which is the length of the element, then we can substitute these values into the approximate assumed displacement function v for a certain node for the total element, and get the unknown values of the constants c1, c2, c3, c4, which are present in the assumed displacement function. Okay, so let's start with the shape function. I'm going to write here shape function derivation. So the first step, of course, would be applying all the boundary conditions in the problem. So we know that if we are going to consider substituting xi is equal to 0 and xj is equal to L in V, that means we will have at I xi is equal to 0 That means V at I is given as ui1 is equal to C1. That's quite easy. Then ui2 is equal to derivative dv dx. That means we can write here, first we find out dv dx, which is c2 plus 2c3x plus 3c4x square, and when x is equal to xi is equal to 0, we get c2. Therefore ui2 is equal to c2. So these are two important solutions or results that we were looking for node I. Now in the same way, we are going to continue to describe for at node j. So we can write at node j, v is equal to uj1 is equal to c1 plus c2x plus c3, in fact this will be xj, c3xj square plus c4xj cubed. Now at node j, xj is equal to L. Therefore uj1 is equal to c1 plus c2L plus c3L square plus c4L cubed. And exactly in the way before that we did, we have u and uj2 is equal to dv dx, which is equal to c2 plus 2c3x plus 3c4x square. And again at node j, xj is equal to L, therefore uj2 is equal to c2 plus 2c3L plus 3c4L square. So I have 4 equations now, and I have 4 unknowns. So if I solve for the 4 equations simultaneously, then I will be able to find the unknowns C1, C2, C3, C4 in terms of nodal displacements. So I'm going to number the equations. This was equation 3, this was equation 4, and on the previous page we had equation 1 and equation 2. Now I'm not going to solve this in details, but if I simultaneously solve equations, I'm going to write it here, simultaneously solve equations 1, 2, 3 and 4 to get C1, C2, C3 and C4. I'm only going to write the solution for these coefficients that were unknown. So C1 is of course equal to ui1, we already know that. C2 is equal to ui2, which we also know. C3 is equal to minus 3 ui1 by by L square minus 2 ui2 by L plus 3 uj1 by L square minus uj2 by L. And C4 is given as 2 ui1 by L cubed plus ui2 by L square minus 2 uj1 by L cubed plus uj2 by L square. So these are the 4 unknowns that we were looking for. If we substitute this back into the assumed displacement function and rearrange them in terms of coefficients of nodal displacements, that is ui1, ui2, uj1 and uj2, we will be able to get the shape functions. So what we want to do here is that we are going to substitute this into the equation which we took as assumed displacement function. That means v was equal to c1 plus c2x plus c3x square plus c4x cubed. So we will substitute the c back here, and then reorganize it in such a way. And then we write here reorganize, so that V can be written as something times ui1 plus something times ui2 plus something times uj1 plus something times uj2. And these somethings are basically the shape functions for the element, or for the beam element that we are trying to derive. If we do that, then we get n1 to be equal to L cubed minus 2lx square plus x cubed whole upon L cubed. N2 is equal to L square x minus 2x square L plus x cubed, the whole thing divided by L square. N3 is given as 3x square L minus 2x cubed by L cubed. And finally N4 is given as x cubed minus x square L by L square. Please work this out yourself as well and check if there's something wrong. Then please let me know if I need to correct anything in the lecture notes as well. Now these are this is the derivation of the shape functions for the beam element. Now after deriving the shape functions, we are able to describe the displacement function that is assumed for the behavior of the element in terms of the shape functions. Now the next step in the stiffness matrix is the stiffness matrix formulation in itself. Now if you remember, we derived the stiffness matrix or the entire equilibrium equation for a finite element by making use of the total minimum potential energy approach. Now the stiffness matrix that was derived within the whole equation only depended on the strain energy that was part of the minimum total potential energy equation. So let's start by getting to the strain energy of the system for this element. To get to the strain energy of the system, let's just first describe the strain energy. So I'm going to write here a derivation of the stiffness matrix. That's quite important to remember. And the first step thereof is to find the strain energy of the system. Now we have done this several times before, so I'm going to start with the definition of strain energy for an element. Gamma is given as integral of over the volume of E epsilon square by 2 dV. So this is the definition of the strain energy in the system. Now here the only unknown that we have, or E, is basically the material property which we know of. It's generally a constant, so we can take that out of the equation. So we have E by 2 volume integral of epsilon square dV. Now it's important to derive therefore what the strain of the system is. To derive the strain of this system, let's get back to the elementary beam theory of the basic assumption that for any beam that is under bending, we'll assume a certain shape, somewhat like this. Goes better than my drawing, I hope. That if this face is AB, then this face is also AB and it remains straight. So if it remains straight, then it is tilted at a certain angle, where this angle is theta, which was already defined as the change in vertical displacement per unit length. So if I blow it up and draw it correctly or much larger, then I know that this was the reference and this is what it became when it was, this is what it became when it was rotated. And the change in neutral axes, let me draw this with a different color. The difference in the height from the neutral axis to the base is given as y, and because it's downwards we write it as negative y. And this angle is nothing but the angle theta, which is given as dv dx. Now the strain of the system is always given as the change in axial displacement over the length. So now if you look at the axial displacement, the equivalent axial displacement in a beam, a bending deformation, then we can say that it can be written as minus y times the angle theta, which is dv dx when theta is really small. So you have u is equal to minus y dv dx. Therefore, the strain is given as minus y d square v dx square. So now we have the derivation of the strain for our given problem. Now we can substitute this back into the strain energy equation. So if I mark this as equation 1 and this as equation 2, then I can write, substituting 2 into 1, we get strain energy of the element to be equal to E by 2. We will always, of course, keep it in volume in the beginning, and we have the negative y, but it will be squared. That means you have minus y d square v dx square whole squared times dv. Now dv can easily be broken up into two parts, which I will show you in the next page. So I'm actually going to write the strain energy equation once again, just to maintain continuity. So the strain energy was given as volume integral of E by 2 minus y d square v dx square whole square dv. Now this I can write, I will write the integral over something later. I can write this as d square v dx square times dx multiplied by an integral y square, but the minus sign can go away under the square, times dA. So that means I have disintegrated or I've actually decomposed the volume dV into dx dA. So the integral here becomes over the length L, and here it becomes over A, the area. Now we know that this part is equal to the second moment of area, or the moment of inertia, as we know as I. That means we can replace it by I. The second derivative of the displacement can now be expressed further, so I can write this as integral 0 to L EI by 2 d square v dx square whole square dx. Now let's get this term sorted out for us. Now we know that d square v dx square is given as the dx square of v. Now the v, if you remember correctly, or let me scroll back to that, the v can actually be described using this relation. So we can write the d square v dx square to be equal to d dx square. If we are writing in a sort of a matrix vector notation, then you have n1, n2, n3, n4, which are the shape functions associated to the degrees of freedom ui1, ui2, uj1, uj2. Or if I want to write it in a very compact form, then I can also write d square v dx square as b times u. Of course, this vector can also be written as a box, like a one row matrix. Now here, the b, of course, where b is equal to b1, b2, b3, b4, which is basically equal to d dx square of n1, n2, n3, n4. If you remember, n1, n2, n3, n4 were all dependent on x, so we can differentiate it twice with respect to x to get the matrix B. So now we have d square v dx square is equal to bu. Now the squared term of the strain should be substituted back into the strain energy equation. So which is of course coming back from here to here. So I'm going to use the bu notation that means here back here in square. So therefore I can write it as the strain energy E is equal to EI by 2 integral 0 to L B U B U. This is the square term times dx. That means we can also write this as EI by 2 integral 0 to L U transpose B transpose. I'm just taking off the brackets to write it much easier so you can see it clearly. So I've just transposed these two terms so that when U comes in front it has to be transposed and B goes to the back it has to be transposed again, and the rest remains the same, B transpose B times U. So this is what it simply becomes in this case. Now we can go back to, so we have this as the final relation, and we can go back to minimizing the strain energy of the system to derive the stiffness matrix of the beam element. So if we minimize the strain energy for the element by means of the displacement, of course there will be 4 different degrees of freedom, so 4 different displacements. You can minimize it partially by differentiating it partially by, of course, but we can do it in one go in terms of using the vector. So we know that the U does not depend on X actually, so we can get it out. So you have EI by 2 and you have 2 times U here. So generally if you would break it out into an equation, you would always get a U square. So instead of using that, we will just make this U square instead of U transpose U. So that means we will end up with a 2 times U as a differential, partial differential, with what is left over is then the integral of 0 to L B transpose B dx. So of course this goes away, and to make it look better, and because when we set it up in terms of the stiffness matrix, it will be much easier to look at, and of course we can write it then as 0 to L. So EI 0 to L integral B transpose B dx, and at the end we write the vector U. Of course this is the vector U. So this is a very compact way of writing it. If you would solve B transpose B, now we know that B transpose, I'm going to bring it out here to explain, B transpose B. Now we know B matrix is right here, 1 by 4, so you have 1 row and 4 columns. So you can write, you know that B matrix is 1 by 4, and we know B transpose therefore will be 4 by 1, so the resulting matrix will be 4 by 4. So you would end up with the minimized strain energy, which is nothing but resulting into the stiffness matrix times the displacement. So basically this part is the stiffness matrix, can be written as EI times a certain 4 by 4 matrix, which I will fill up for you for your ease. It will always be divided by L cubed, so I'll take the L cubed out. You can write it as 12, 6L minus 12, 6L, 6L, 4L square minus 6L, 2L square, minus 12 minus 6L, 12 minus 6L, 6L, 2L square minus 6L, 4L square. That is your 4 by 4 matrix coming out of B transpose B multiplied and then integrated from 0 to L and substituted 0 to L. And then finally the displacement vector, which includes all the degrees of freedom, as we know that we have defined for the beam element. So this is giving us K times U. Therefore the stiffness matrix for a beam element or for pure bending condition is given as this. So here we have derived the stiffness matrix for the beam element. So we used only the first part of the minimum total potential energy, because if you remember, the total potential energy was given as a strain. So you have summation of strain of all the elements minus the work done, the summation of all the work done for all the nodes, and that would be equal to 0. So what we have already gotten is Ku, and what we still need is the F, or the force vector, to set up the entire equilibrium equation.